So we've been working with exponential growth, but now it's time to work with its compatriot, which is exponential decay. If you remember, when you have an e to the kt, if you let your k value be negative, as it is over here, you can see that it is an exponential decay model. Right? That curve is decreasing. All right, so exponential decay would still have a y0, which is the initial amount. Right? That part hasn't changed. It's not generally called the principal. I mean, if it's in finance, but hopefully you don't have your bank account decaying. Although maybe your debt would be decaying. And the constant k, well, we just saw it would be less than 0. It would be negative because it's decay, as opposed to growth, which is greater than 0, although not equal to 1. Now, the constant half-life now is t 1/2. Now, if you remember, we were interested before in doubling time. Doubling time is t2, right? Capital T2. It's a constant, right? So this is just a constant for some model. Every model has its own doubling time. So in growth, we're interested in doubling time. In decay, we're interested in halving time. So the amount of time it takes to reach a half of what we started with, which, very similar to the doubling time, would be the natural log of a half divided by k. This is the formula for the time it takes to reach half of what you started. All right, so let's do an example of this. Classic example, everybody's done this in an algebra class, which is radiocarbon dating. Now, carbon-14 is a radioactive isotope that's present in all living creatures in Earth, right? So, and when the creature dies, then it starts ceasing to gain or replace their C14, and it starts losing it slowly over time. And carbon-14 has a half-life of 5,730 years. So this is in fossils, it's bones, etc. So this is one of the ways that we can find out how old things are. So we're going to find a formula that represents the amount of C14 left in a bone at t years. Interesting. Okay, so let's start off with the beginning amount. C of t, and you might be thinking, well, they didn't give us an initial amount. All right. In science class, they usually will. They'll say, this creature had, 7 grams of carbon-14 at one point. And so you'd use the number 7. But for our purposes, we're going to start off with 100. So we're going to let me put it this way. Let me write it this way. We are going to let C of 0 equal 100. Because the organism had 100% of C14 when it died at t equals 0, right? T equals 0 is the time when it died, right? That's the beginning of the losing of the carbon-14. So that would be time 0. All right. So then C of 5,730. After 5,730 years, it should be half of that. So it would be 50. Now I know I could use the formula up above to solve for k, but I just want to prove to you that this will work. So I'm going to do it a different way just to show this, but you could absolutely use the formula. All right, so I have 50 now. I have half of what I started. I started off with 100%, and now I'm at 50%. And it took me 5,730 years to get there. Or this bone, 5,730 years to get there. All right, so now I want to solve this for k. So I'm going to start by dividing by 100. And lo and behold, 50 divided by 100 is a half. Like the half in the formula, see? So you'll have a half equals e to the k times 5,730. Now, of course, you want to solve this for k, so you want to get that k out of that exponent. And the way we do that is we take the natural log of sides. That brings that k times 5,730 down due to the power properties of logarithms. Sorry, that's a little tight in there. Let me make this. So you got your log, and then this comes down in front. I think it made it worse. There you go. That's a little better. All right, so the natural log of e is not going to mean anything. And over here, I'm going to have the natural log of a half equals k times 5,730 times the natural log of e, but the natural log of e is going to be 1. That's why you're doing a natural log as opposed to another logarithm. So then k would be equal to the natural log of a half divided by 5,730, which is, I found it in Desmos, in case you missed it, it was there. It's negative 0.00012. That's good enough. So we'll give it a squiggly equals, an approximate, and call it a day. So therefore, C of t is equal to 100 e to the negative 0.00012 t. We've found the formula. Now I want to make a note. We actually didn't have to do it this way. This is kind of more an algebra way to do this, but I want to make a little note over here. We know that the t half-life time is 5,730, and we know according to this formula right here that that's the natural log of a half divided by k. So that means that k is the natural log of a half divided by 5,730, which is negative 0.00012. So you can do it that way because we know that formula for half-life. This is why it works involving the algebra. But we're not an algebra class, so you can kind of skip over all this if you want to and get to the Ka value right there. That's totally fine. That's fine. All right. Now part B. Part B says a well-preserved piece of wood found at an archaeological site had 4.7% of the C14 that it had when it's alive. Estimate when the wood was cut. Okay, so we now have 4.7%, and we started off with 100%. And so we're just going to use a little bit of algebra, right? We'll divide both sides by 100. That's just the smart way to go. And you'll be left with 0.047. It moves the decimal 2 spots over when you divide by 100. E to the negative 0.00012t. And again, we're going to take the log of both sides. This comes down in front. So it's the natural log of 0.047 equals negative 0.00012t times the natural log of e, but the natural log of e is going to go away, so it's irrelevant. So t is the natural log of 0.047 divided by negative 0.00012. So I want to take the natural log of 0.047. I'm going to divide that by, now technically I'm dividing it by all of this, so I could just copy and paste that in there, and I'll get 25,276. Now if I take the natural log of 0.047 and I just divide that by negative 0.00012, I've lost a little bit of decimal places of accuracy. So for our purposes, I guess we'll stick with the decimal because that's what the book does. So we'll say it's 25,480. It shows you how quickly you can lose accuracy on these half-life problems. You really can. That's why historians that work and archaeologists, they'll always say, you know, a window of, 25,000 to 26,000 years. This is why they do that. One of the many reasons. All right, so we'll just say it's that many years old.